So I thought I would just give a couple of, or a slide, no, 2 slides explaining who I am, because with someone saying, oh, are you the physicist or the real physicist here, is kind of slightly intimidating. So this is a bit of time travel in itself. So I got my PhD in theoretical physics from Cambridge. And then I spent 5 years as a researcher in Chicago, partly at Fermilab and then at the university. I came back to the UK on a long-term fellowship, and I'm now a professor in both mathematics and physics at Durham, and my research is in gravity, cosmology, and extra dimensions. So I hope you can recognize that that's me there. Keep fingers crossed. However, really, I think if I have to, so when I get asked what do I do when I go to the US, actually this is what I tell them. So sadly, it is exactly what Sheldon Cooper does, pretty much. That's the sort of thing I do. But at least it paints a picture for them. And I have to say that show is, in many cases, frighteningly not an exaggeration. Okay, so all I'm going to do now is just say a few things. This is going to probably be possibly technical for some of you, but maybe not. I always think it's a good thing anyway to just see how how scientists actually go about thinking about the issues. Because I think what I've found already in terms of the first 2 speakers is that I can identify structurally similarities with many of the things they've been saying. The difference is, in science, we try and formalize it, which often means putting things in terms of a framework or equations. So but many of the structures that have been talked about, actually, to me, I can say, oh, yes, that's that particular thing, or, well, what they mean is this. So just to be a reminder, what do we mean by a dimension? A dimension is just a degree of freedom. I'm talking about extra dimensions. I just want to give you a context for what that is. So usually, we imagine dimensions as being spatial dimensions, and I think that's sometimes why there's some confusion when we start talking about time. So a spatial dimension is side to side, here's 1 degree of freedom, forwards and backwards is another, and then up and down. So that's 3 degrees of freedom. But actually, mathematically, we can have as many as we want, and there's absolutely no reason that we can't do more. So time is also a dimension. So I don't really think of time as being so radically different from space, although it is different, because we experience it rather than directly see it. There is a difference in the way we actually measure time. And as Layla was saying, we do seem to be rather obsessed with the measurement of time. Although in the field that I do, I wouldn't use days. Days are actually arbitrary as well, because they depend on the mass of the sun and how far away we are, how fast the Earth's rotating, days, years. So in my area, we talk about Planck times, which are an insanely small unit of time. So you'd have to multiply them sort of 10 by itself 44 times to multiply the Planck time to get 1 second. So these are sort of fundamental units of time. So time itself mixes with space. You probably heard about relativity, but Einstein told us, in fact, space and time are sort of really part of the same thing, which we call space-time. So really, that's where I work. I work with space-time rather than thinking about them separately. And so as we have the sort of classic things of relativity, as objects move very fast, we think they're shorter, they look shorter to us, and we think their clocks are running more slowly. So these are some of the things that happen in terms of theoretical physics, well, or practical physics, actually. So extra dimensions. What do I mean when I say I work with extra dimensions? it's actually exclusively, we mean extraspatial dimensions. There's only one instance where we even think of adding another time. So basically, what we mean is we've got more than 3 space dimensions. So we're adding new directions in which to move. So although, again, I said we can do that from a point of view of maths, we can sort of do what we want, really, when we're playing games with symbols on a piece of paper, but why would we do it? Well, the reason why modern theoretical physicists add extra dimensions kind of goes back again to Einstein, but more the legacy of Einstein. Einstein wanted to unify all the theories of interactions into one big unified field theory. He didn't manage to do it because he was never really comfortable with quantum physics. There's a great quote. Einstein used to say, "God does not play at dice," at which a famous quantum physicist, Niels Bohr, told him to stop telling God what to do. But nowadays, it's not completely conclusively proven, but we have a fairly good stab at unifying gravity with all of our other quantum interactions. And this is, again, if you've been watching Big Bang Theory, you will have heard this, superstring theory or string theory. And string theory replaces our notion of interactions of particles by interacting strings. And it's a way of making gravity quantum mechanical. There's just one little snag. It seems to work in 10 dimensions. So 10 is 1 time, 9 space. So we have extra dimensions. So what do these extra dimensions mean? Well, it's a bit of a problem, really, because you saw me just go side to side, forwards and back, and up and down. And I didn't do another 6 movements, at least not that I'm aware of. So we can have extra dimensions, provided we hide them. And so in the end, we're playing a bit of a game like the TARDIS, because what we're trying to do is we're trying to say that something is somehow either small, which is the way we used to hide them, or something a bit more recent is where our internal dimensions can maybe be a bit bigger, but they're hidden because we are confined to something called a brane world or a slice. So I'll try and get across a little bit about what that means, and then I'll talk a bit about black holes. So confinement sounds weird. You might think, what does it mean confining yourself to some slice? Well, you can, if you've read about flatlanders, it's that sort of notion. You're sort of flat compared to these extra dimensions. But I tried to think of a more practical analogy of confinement. And in fact, I realized we know about confinement all the time. Confinement is simply saying that our particles, our sort of normal physics, would rather be here on some slice than everywhere. And that's really what we do. We like to live on land, or if we're in the middle of an ocean with sharks, we would want to go on the life raft. So confinement is simply an analogue of a region in which life looks a bit better, or in which particle physics goes on the way we expect it to, and it's really hard for that physics to go on over here in this bigger set of dimensions. So it's a bit, obviously, a bit more complicated mathematics, but it's that sort of notion, it's that concept. Things will exist where they can. So what happens to gravity? I haven't it's obviously 20 minutes as a brief talk, but I want to sort of try and talk a little bit about implications of extra dimensions. So what is gravity? Gravity is the most ubiquitous force that we experience on a day-to-day level, and it's the one that we take most for granted. So every day, every step of the way, we are being sucked down and pulled towards the center of the Earth. So that's what gravity is. And it was first made quantitative by Newton. Newton told us that gravity is what we call an inverse square law. What that means, if you can see, is that the force is proportional to the square of the distance between the two objects as well as their masses. So why the square? I'm going to labour this because of the extra dimension bit. The reason for the square is essentially because you're spreading the effect of gravity out over spheres at a fixed radius from the source. And so as you go from 1 to 2, a single square will now look like 4 squares. From 1 to 3, it's going to look like 9 squares. So hence inverse square law. So that's the idea of what Newton's gravitational force does. So what happens if you have more dimensions? Well, by this sort of notion, if you had a Newtonian gravity, instead of a force being proportional to 1 over r squared, you'd start getting extra powers of r. Because in, say, one more dimension, your sphere would be 3-dimensional, so you'd go 1 over r cubed, and so on and so forth. So gravity changes as the number of dimensions change. So what might this do? Well, one of the objects that we love playing with in theoretical physics is a black hole. So what's a black hole? Well, a black hole is something that's so massive and so compact that the escape velocity exceeds the speed of light. So what is escape velocity? Well, this is sort of again using physics concepts, but you can escape the planet when you have enough energy to sort of buy your way out of its gravitational well. So it's saying a kinetic energy, the energy of your motion, is going to be equal to the gravitational energy that you've got to spend to climb out and escape from the Earth, say, if it was us. So kinetic energy, good old Newton again, is a half mv squared, just sort of zen if you don't like equations, that's okay. And then Newton's potential energy is this Newton's constant, a couple of masses, and this magical r again, the distance, how far away from the centre of mass you are. So if we pop in v equals c, we find that there's a very special radius where the escape velocity is the speed of light. And this is something which characterises a black hole. It's actually the very same number when we do it in full general relativity, and it's called the event horizon. So what does Einstein's gravity do for us? Well, very briefly, things that happen is it's kind of what Einstein's relativity does is it tells us that instead of being very rigid, our space-time is kind of quite it's deformable, it can curve, and it also tells us that time is slowed down in a gravitational field. So why is that? I just said we have to pay energy to get away from the Earth or from any gravitating object. So if we try and escape from the Earth, we lose energy by paying off this gravitational bank. On the other hand, quantum physics tells us if we lose energy, then say if we're looking at light rays, the frequency of the light ray will drop. So light gets redshifted. And so this is a sort of little sort of animation showing that. But you could imagine a clock, and in fact this is how sort of, well, partly how, it's not quite light rays, but essentially oscillations are sort of counting a tick of a clock. And so if they're becoming slower, time is becoming slower. Now in fact, Newton's gravity could have told us that there was gravitational redshift. What Einstein does is relate that to a property about the sort of stretchiness. Oh, sorry, I'm going to end up like Doctor Who here, timey-wimey, wibbly-wobbly stuff. It's sort of, it's coming out a bit like that. But it's basically, in general relativity, we use this space-time as being a dynamical sort of object. It warps, it deforms, and what deforms it? Energy of any sort, not just matter. Any sort of energy deforms the space in which it lives, and space-time. Now, of course, a black hole is black, so how do we see it? Well, we kind of deduce it's there. And so one of the interesting observations of the past couple of decades is that at the core of our galaxy, there's a supermassive black hole, and that's been put together by very carefully tracking orbits of stars that sort of come round and then whip past something. From the orbits, you can see it's something very, very heavy, about 1 million odd solar masses, and the stars are going so fast you can see where it is that you can kind of deduce there's no way with known physics that that thing could be anything other than a black hole. So the black holes are, black holes are sort of crop up in science fiction a lot simply because they are really quite exotic objects. They're the strongest gravitational objects that we know, and if light can't escape, nothing can. So that sounds rather... So of course you've got to write a way around that, your hero's got to come back. So I thought I'd just sort of bring the theme to Doctor Who and talk about a couple of things from Doctor Who. So one of the things that intrigued me when this particular show was broadcast it's I guess the season 2 of the new Doctor Who with David Tennant and Billy Piper. I'm sure I was called a Billy Tyler there for a minute. They got marooned on a planet which is allegedly in orbit around a black hole, and it was called the Impossible Planet. So, well, that's a red flag to a scientist, obviously. Is it really impossible? So I thought I would just, for those of you that don't mind the odd equation, tell you, yes, actually, it is impossible. So from the picture, if you look at it, I was looking at it on the show and I thought, that looks like the sun, doesn't it? Yeah, that's about the size of the sun in the sky. So I figured, right, so that's about a degree. So I'm going to use the same estimate for the sun. But then, that allows me to give an estimate for how far away from the object you are. And then I can estimate the forces that are going to be acting on this planet due to tidal forces. We know about tides, even if you don't like equations, tides, the sort of moon kind of pulling the sea around. So I can estimate what the tidal forces are. And so if this was a regular stellar mass black hole, which honestly, from the way it was sucking up the gases in the accretion disk around it, I would say it probably is. Then I get a tidal force, which means the difference in gravitational acceleration from here to something a meter away here is 10,000 meters per second squared. Now, G, that's 10 meters per second squared. That's a wee bit of a difference, okay? So I think that planet is definitely impossible. However, if it was a supermassive black hole, it would actually be possible. So I found, Doctor Who can be this wonderful mix of, really rather, you think, oh yeah, they've done their homework there, and then, oh no. Another thing you might have heard of, a black hole catastrophe, is because what happens as you add extra dimensions, you're essentially weakening gravity relative to other forces as far as we're concerned in our little life raft, our confined brain. It means it becomes easier to form black holes. And so for a while, well, I mean, not for a while, it is actually part of a simulated sort of event generator that these people do for the LHC. They do actually try and model creation of black holes, but for a while somebody actually tried to sue in the US to stop the LHC being switched on in case it destroyed the Earth. But they kind of were missing the physics because, of course, the same quantum physics that allows us to create it is going to let it evaporate. So even if it forms, it evaporates more easily. And in fact, the sort of things that the people were trying to work out at the LHC were evaporation rates so that they could sort of pop it into their calculations. So don't move planet yet as the sort of... So just to sort of finish off time travel, I've really sort of focused more about aspects of dimensions and extra dimensions. So what would we really mean by time travel? in general, anything going faster than the speed of light is time travel in a certain sense. But what we really mean when we're talking about Terminator or Back to the Future, we really mean what we would call, technically, this is a good technical term, a closed time-like curve. So that's what we scientists would say about time travel. This is what we're looking for. So if we want to construct something, again, within the rules of the game that we have, that has a closed time-like curve, you find we tend to need negative energies, which doesn't sound very good, does it really? But actually, you can have sort of negative energies in quantum theory. So, you might think, hey, you guys are going to tell us we can go back and kill Grandad. But every known example that physicists have tried to construct is either unstable or it sort of leads to very bad physics, which is, I think, saying essentially the same thing that our previous speaker was saying, in that either you have to have this closed curve where everything happens and it always happens, or everything goes radically wrong. So sadly, I can't stand here and tell you that we know how to time travel, but for the moment, Time Lords still remain in the realm of science fiction. But I have to say, I wouldn't really mind if we suddenly discovered there was some new physics out there, because I think the world would be a lot more fun if we could travel faster than light. Okay, thank you.